I wish this didn't kill my machine so much when I ran this program. Let me check. Windows seems to have taken out the run with graphics processor option. OBS Studio, high performance. Oh. Well, it is what it is. It is what it is. Where is the Twitch? Oh, there it is. Hello, hello. Hello, hello. All right. Look, I have Photoshop. I have all sorts of things. Okay. I was going to do some hash table stuff today. Yes, Windows 98. Back when things were so much worse than Windows 10. Oh my goodness. Oh my goodness. Okay. I had been watching a YouTube video recently with a discussion from some people. And they're talking about hash tables. And coincidentally, somebody in the beta program had made a feature request about hash tables here. So I was like, maybe, and we use hash tables a lot in the game. So I said, maybe I should look at this a little bit. And I don't even remember what the feature request was now, because I do a lot, and all these things happened at random times over the past week. So over the course of the stream, I'll be reminding myself of the things. Anyway, though, I was looking at the hash. Okay, so hash table, what is it? It's basically an array, like a flat array, that you use to store things that you want to be able to look up quickly later on, right? And how do you do that? Well, you have a thing called a hash function that you use to like scramble the data, whatever data type you're trying to look up. You turn that into some integer, and hopefully you turn it into a very different integer than it would be for any similar data, right? So the hash function's job is to make a number that looks random out of data that's very deterministic, right? And then that number is used to determine a slot in this table, and that's where you put the thing, right? So even if you have 1,000,000 entries in your table, hopefully the idea is that you can scramble your input data, which is hopefully a lot smaller than the table. Otherwise, this doesn't make that much sense. Actually, it might still make it. It depends. So you scramble your input data with the hash function. use that to find in the table where to look, and then you look there. And ta-da, your entry is magically there. However, this doesn't always work perfectly, right? Because even though the job of your hash function is to make something that looks random, it doesn't always do that. Or it doesn't, like, even if it's perfect at making things that seem random, if things seem random, then sometimes you'll roll the same die twice, right? So that's a thing that happens. But also, you want to store things in a relatively small table, otherwise you use infinite memory, right? We don't want to use infinite memory in our programs generally, unless you're in functional language class in computer science school. But that is not where we are today. So you tend to want to use a reasonably small table, and that means that you do something once you get that random-ish integer to map that integer to your table, like you just mod it by the size of the table or something, and that can cause different integers to map to the same slot, right? So then you have a strategy for how to deal with that in your hash table. And there's sort of two major different ways that you deal with this. One is to, instead of just have every slot be one data element wide. Like let's say we're storing strings in the hash table, right? Instead of having each slot just point to one string, it could point to like a linked list of nodes that point to strings. And that lets you put as many things as you want in a bucket, right? Now that becomes a little bit sad if your bucket gets a lot of strings in it, because suddenly you're doing like an order n search, and you didn't want to do that. You wanted something faster than order n, right? The idea behind a hash table is that it's roughly constant time in the size, in the number of elements in the table, right? And the main cost is just hashing your data, and if your data is fast to hash, or even if you store the hash, then it's very fast, right? Okay. Now, I don't do things that way for the hash table that we give out in the library of this language, and many people don't do it that way, because the problem is you're adding things to the hash table in random order, so you may add things at relatively different times. And so when these little memory nodes go into this list, they're likely to have been allocated relatively far from each other. That said, you could try to take some strategy to mitigate that, like every bucket has a memory arena or something, and you only allocate things sequentially out of that. That seems like a very difficult strategy to make pay off, and it seems like it would complicate your code by a lot. So an alternative strategy that people do is instead say, instead of having a linked list in every slot, we are just going to, if you look to try to store something in a hash table, and there's somebody already in the slot you're trying to use, then just pick another slot, right? And you need some way to pick another slot that can be reproduced later when people are going to look up the element, right? How do you do that? Well, the dumbest idea is just go to the next slot and go to the next slot. Well, you guys are go to the next slot, go to the next slot. That's not that good of a strategy. I actually, because I thought that it wouldn't be that bad, I just shipped that strategy initially to the beta users, and that's why this is a beta, because it turns out that fails pretty badly for large hash tables, like worse than I thought. I thought, like, okay, if you have this strategy where you just go to the next one and go to the next one, then obviously that could end up kind of slow if you get multiple collisions next to each other, because they'll both run together and make like a long sequence through the table, right? Okay, here's the difference between these two strategies. In that linked list bucket strategy, if you add more buckets and make your list longer for that one slot in the hash table, you're only ever affecting people who map to that entry in the hash table. They will all get slower in a way that makes you sad, but only those entries that map to that slot will get slower, right? Oh, you know what? I didn't finish the memory. Okay, the reason why it's bad to have these buckets that are allocated at different times, sorry for skipping around. The reason that that's bad, many viewers of this channel will know, is that you will have bad memory locality, right? Like they'll be located in different cache lines, possibly quite far away from each other, depending on how you allocate the buckets, your nodes, or whatever you want to call them. And that means that every time you go down this array to look for your element, not only are you order n traversing this array, but each step, or traversing this linked list, but each step in walking down that linked list is going to be very expensive because it involves waiting on memory, and there's nothing you can do till the memory comes in, right? So all that makes you sad as a programmer. So that's why we're talking about just using other entries in the hash table, right? But that introduces this problem that if you spill over to another slot in the hash table, now you're expanding into space that somebody else wanted to use, right? And so a different hash entry can now collide with you not only on the original slot that you tried to use, but also on the new slot that you spilled over into because you couldn't use the original slot, right? And now, when I was originally thinking about this and shipping the original version of this hash table to the people, I was just hand waving and saying, oh, it's not really going to matter. We'll just spill over into the next slot because I don't see any reason why any other strategy would be better than that, because all slots in the hash table are kind of on equal footing, right? Like, why do they care about each other? They're sort of like randomly mapped to. And what I didn't understand at the time was there's this problem with the birthday paradox. And you can go look on the Wikipedias. Oh, I already have it. You can go and look on the Wikipedias. It's not a paradox, really. It's called birthday problem. So this is a thing a lot of people get introduced to in grade school, or if you have a class with like 30 or 35 people in it, you go around and you, with high probability, you find that two people have the same birthday, right? Let me check my camera for a second. Yeah, okay, it's good. You find that people have the same birthday, and you find two people who have the same birthday as each other, right? It is not very likely in a group that somebody shares the same birthday as you specifically, but because there's 365 days in a year or whatever and only like 30 people, but it is highly likely that some two people share the same birthday as each other, right? And you can read about why that is here. It's a thing that many of us get introduced to when we're young. Okay. So you can figure out how that's computed. Now, that is the same as asking about whether two entries collide in a hash table, right? Because the width of the hash table is the number of days, right? And the hash function generated mod the table size, or however you map it to the table size, is the birthday of the entry, right? And if you make those two definitions, it's exactly the same thing. So the first thing that says is that you will get hash collisions maybe earlier than you naively would think, all right? You will get some collisions in a relatively empty table, right? If you have a group of 30 people in your class and there's 365 days in a year, you get at least one collision with high probability. That seems really weird, right? The table's mostly empty, but that's how it is. So I didn't invent math, guys. Let's talk to God about that one. So so that's an interesting thing to think about, but it affects, if you take this strategy where you just spill over to a neighboring bucket, or any, like you could skip every 2 or every 3, it's functionally the same. You have this problem where there's like a meta birthday problem. Let me see if I could I explained this to someone in email, and because I got up and haven't had enough sugar, my brain may not be online enough to explain it without figures and all these things. But basically, all right, let's try to do a simple diagram in Emacs. All right, so you've got your hash table, and these underscores are going to be empty slots, all right? These are our empty. There's a bunch of them. We're not going to draw hundreds or whatever like you might really have. Okay, those are all empty. I go put something in the hash table. I get some integer. I mod it by the size of the table, and I put it there. Let's call that 1. Okay, I do another one. It comes out here, 2. I do another one. It comes out here, 3. All right. At some point, I get a collision. I do 4. And I try to use the same slot as 1. And that slot's not available, right? So now in the linked list strategy that we just talked about, we would put like a node down here, and then we would put 4, right? And then, I don't know, if 9 went there, and then 12, I don't, you know, then we would jump to this entry and we walk down the list and find the stuff, right? Okay, but we're not talking about that. So if we do 4 here, we try to put it here. We see that's already occupied by 1, so we're going to put it here, all right? Now, if 9 comes along later and maps to 1, we're going to say, oh, wait, 1 is filled. Let's try and put it here. Wait, 4 is there. Let's try and put it here, and we put 9, right? Okay. So you can see now we're making this run longer and longer. We're filling the table with this linear run of stuff as opposed to hanging out a linked list. Now the problem is anyone who maps anywhere into this run is suddenly an O of n search. They all are sort of mapped to the same bucket in a weird way. It's just some of them are further along in the bucket, but we still have to linear search forward, right? Like if, let's just go into alphabet so that it's all only one character. We can use lowercase as well, right? But let's just say A, and then F, and then J, and then L all mapped to somewhere in 149. We would all go forward, and then eventually M and P, we got unlucky for a while, and then that runs into 3. So now if W is here, we're going to go, oh, it maps to 1. Okay, that's filled, 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 that's filled. Aha! Whoops. Aha! Right? So you can see how this would start to get pretty slow. Right? It's memory efficient, but once this starts happening, this is a bad situation. And so you want to avoid this happening. And when I first was going to ship this to the people, I said, well, I see that this could happen, but it seems to me like that the same thing would happen regardless of what the strategy is of how you find another bucket, so I'm just not going to worry about it. And that was me not having enough experience in hash tables. It's not true. There are ways to avoid this. And the reason is, okay, so I kept saying, you know, I just said, for example, what if W lands here? But that's the worst case, right? What if we were going to insert W and it lands here, right? Well, if we had inserted it a long time ago before J, we would be fine. But we inserted it after J, right? So we land here, it's filled, it's filled, it's filled, it's filled, it's filled, it's filled, W, right? So the problem is that we make a large continuous no-no region that's all glued together, and at the end of doing this expensive search, we make the continuous no-no region longer and more likely for more people to hit it, right? Okay. So the thing that makes your table slow is growths of long contiguous regions like this. Now, let's go back for a second before the universe got bad. If we're just looking at 1, what causes this region to grow, right? Under what conditions, if we're going to insert 4, under what conditions do we start making a bad region? Obviously, if we try to put 4 on top of 1, we're going to say it's filled, go to the next slot and put 4 there, right? But that's not the only case in which 4 ends up there, right? What if we don't even collide, but we hash 4 and we say it's some number and we mod that number by the size of the table and it puts us there? Well, that's a little bit better than having to notice that it collides with 1. It's a little bit faster on that insert, but in terms of the content of the table and how the table ends up later, it's the same, right? Like if we're going to insert 5, here we still have to go through both of these guys, even though these guys didn't collide, right? So it's bad if we try to put 4 here. It's bad if we try to put 4 here. It is also bad if we try to put 4 here, because now we made a continuous run, also without a collision, right? So here's the interesting thing, is if you're just going to ask, does 4 collide with 1? That's regular birthday paradox, right? That's just regular. You can look up the math on the Wikipedia page. It happens more often than you would think, but it's that regular thing. Okay, it happens more often than you would think for any 2 elements in the table, not for specific ones, right? For specific 4 colliding with 1, it's normal. It's a very easy to understand probability, right? But, okay, what if you ask, how many slots can I put 4 in that is bad because it makes a continuous run? That is more slots than the birthday paradox, right? Because birthday paradox is only about hitting one of these directly. Here, it's bad if I put 4 here because I make a longer run. It's bad if I put 4 here because I make a longer run. And it's bad if I put 4 on top of 1 because I make a longer run. So that's 3 different cases instead of 1, all right? And that's true for any of these. Like instead of colliding with 1, I could have collided with 3 or put 4 after 3 or put 4 before 3, right? In any of those cases, I create a longer run that decreases the speed of the program. And now I'm a little bit not sure how to think about this, but the thing is, there's a little bit of a feedback loop where it becomes worse, because now that I've put this here, next time when I'm going to insert 5, there's even more possibilities of making an even longer run. Like this, now there's 4 places to put 5 that are all bad, right? And when I put 5, now there's 5 places to put 6 that are all bad, right? The number of bad places for something to go goes up as this run goes up. Now, that said, it's actually maybe not that bad, because the number of bad places to put something, actually, the total number throughout the table grows more slowly if you're making a run longer, because every time you add an empty element to the table, you add 2 bad places to put something if it's off by its own, or 3 bad places, right? Whereas if you add something in a run, you only add 1 new bad place because you expanded the run 1 to the right, and the end of the run and the space after it were already bad. The problem is just the cost of landing in one of these regions is much higher than the cost of like making a 2-bagger here, right? Because these regions get long. Anyway, there's probably some math that somebody has done to like compute the relative cost of all of these things. But it's just to say that growing these long linear sequences is bad. Okay, what can you, I wanted to make one more point about birthday paradox, right? Okay, growing long linear sequences like this is bad. What are the conditions under which you might do that, right? Like if I have a couple collisions on 1, which imagine 1 is any element in the table, we're going to have a couple collisions on it because of birthday paradox, even if the table is very empty, right? Even if the table is 10%, we'll have collisions somewhere probably. Okay. So let's just say A and B, just whatever, even if the table's pretty empty, we'll have a couple collisions on somewhere, right? Okay. And we're calling that somewhere 1. This isn't specifically the first entry. This is just some entry that has the most collisions. All right. What if we do, let's just call it 2. And this is not the second entry. any other entry in the hash table after we've inserted all this stuff, right? What if 2 ended up being next to 1, its neighbor, okay? Now, depending on whether 2 was inserted earlier or later, the order of what I'm about to type may change, but it would all run together anyway. So we would try to insert 2. It's like full, full, 2. And then we have C and D. C goes here, full, 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 C. And D goes here, full, 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 D. All right? So we start spending a lot of CPU anytime you have 2 guys that have collisions that are neighbors. All right, even in a relatively empty table. Like, okay, so the load factor that, like, some academic papers say optimal load factor for hash tables is like 83% or something. I like something like 70%. But keep in mind, birthday paradox, right? If you go to the Wikipedia page for birthday paradox, in a 365-day year, you get a 50-50 chance of a collision at 23. Like way less than 10. That's like 6% or something, right? So you can look up the probability. So in a 365-day year, right, let's say around 36, it's like 87% probability at 10% table occupancy, right? So if you run load factors of like 70, like we do, or 80 or something like papers tell you, it's basically 100% of one. Like by the time you're way up here, it's not just that you have one collision, you have multiple, right? Because that's just what happens. You have many, okay? So if you're not just spewing the memory fire hose, which is slow for its own reasons, because then you get poor cache locality when searching the table, you can expect a bunch of collisions, is what this graph says, okay? So this will happen. The bad situation is when you have people who are neighbors or near each other that have collisions. And the thing to realize is that is also its own birthday paradox, right? So instead of the set of all people that you put in the table, think of just the subset of all entries that collide with each other, which is going to be less than the total number of entries in the table, but still substantial because you have more collisions than you think. Now you have a birthday paradox among those, which is, are any 2 of them near each other? Because depending on the number of collisions, they don't even have to be right next to each other to run together, right? Are any 2 of them near each other? That's a worse birthday paradox, or easier to collide birthday paradox than are 2 exactly on top of each other. Now it's got a smaller n, but like a larger hit probability. And when it happens, it's very bad. And the point of saying that this is another birthday paradox is to just say, this happens more often than you would think it would, right? Because it's a birthday paradox. But it's like it's a 1 level removed meta birthday paradox that you have to think about, right? How is that affected by the cardinality of the hash function? It is not really, because whatever your hash function returns to, it's very common to have a hash function that returns a 32-bit number or a 64-bit number, but you always have to map that down to the table size. Table size ain't going to have 4 billion entries, or these days it might in a very big table, but it ain't going to have 4 billion squared entries. That's just not a hash table that we do, right? That probably doesn't fit in the universe, right? Or sorry, not even, yeah, I don't know. Yeah, it's like an avalanche. I don't know a lot about avalanches, but that metaphor works for me. Okay, so what do you do about this? Well, the deal is, instead of spilling over to the neighboring space, by the way, we could, if you want an exercise at home, you can just draw this out. Like, what if the strategy is to skip 2 every time, right? Well, you get the same problem. It's just mod 2, and you could convince yourself of that, right? By the way, if you put something here, right, if I insert 3 at the end and I try to insert 4 on top of it, what do? I just wrap around to the start of the table, right? So the start and the end of the table are not really special with regard to anything. Okay, so what is a different strategy? Well, the thing that you can do is anything that would cause neighbors not to run together for very long. All right. And now I'm just going to try, I've never tried typing out the probing strategy that we use by hand, so maybe a surprise will happen here. But I'll show you first what strategy that we use. So here we go. So this says if the hash is non-zero, we store the hash in the table along with the data element because it's a fast way to know if you have a collision or not without having to compare the data elements, right? Since the data elements might have like some user compare function that could be relatively slow, we just say, are the hashes equal? And then once we do that, we can also say hash of 0 is reserved. So hash of 0 means that entry is empty, right? Hash of non-zero means it's full. Now the problem is if you have a user hash function, it might return 0. So we just add 1 if the user hash function is 0, which makes one of the elements in the table double probability of collisions to the other ones, which is interesting because it adds some anisotropy to the table. And I haven't really, I hand waved and said, oh, the consequences of that probably aren't that bad. But honestly, I haven't thought that hard about it. And what I have seen about hash tables is if you haven't thought that hard about it, you may get surprised. So that's maybe a potential surprise. Maybe if you do it in reverse, it could be faster. No, reverse is isomorphic to forward, right? Like it's just the same. Okay. Now, by the way, when you have a hash table, what everybody talks about is like, what if your hash table, your hash function isn't good enough and generates a lot of collisions? That is a thing to worry about for sure. But everything that I've said so far happens anyway if you have a perfect hash function that is, as far as you can tell, generating completely random numbers, right? Like this is just a mathematical fact about putting entries into a small table, regardless of the quality of your hash function. If your hash function is worse, then your results will be worse. But there's like a bound on how good the results could be. And people who are not familiar with the subject matter can get surprised by that, right? They could, you know, because you sort of imagine, like I sort of, you know, I don't want to blame other people. Like I sort of imagined, well, if the hash function gives you random numbers, you're not going to have that many collisions in a table that's only 70% full. Wrong. You have a bunch of collisions. Okay, so what we do is we have this probe increment that starts at 1, and that is where we look next for the next entry, right? And so it starts at 1, which is just exactly that strategy that I said of going over to the next entry, right? But we add 1, so we check the entry at index. If it's occupied, meaning the hash is not 0, we add our probe increment, which starts at 1, so we go to the next entry, right? But then we increment the probe increment. So probe increment becomes 2, right? And then if next time around, and then we wrap around the table here, right? And we say while because what if the probe increment is really big relative to the table size? Hopefully that never happens, but you know, it is what it is for now. Anyway, so if probe increment is now 2, we went to the next index. This is also full. Now we add 2 instead of adding 1, right? And then we increment this to 3. And then if that's full, we add 3, we increment it to 4. So we keep skipping further and further ahead, right? Now the further and further is not necessarily that important, actually. In fact, it's actually bad, because if you start skipping really far, you have bad cache coherency, right? But I wanted a simple way to have the probe increment change in a way that makes 2 neighboring entries diverge from each other. And we're going to go look at that and hope that that's true, right? Okay. Because I haven't actually looked at what happens. But you know, a different way that you could do this is you could have like a data table somewhere that you read the entries of that's pre-generated. I didn't really want to do that, but if that's a substantially better strategy, maybe we should. I don't know. The thing with that is, oh God. Dude, we're trying to have a session here, Microsoft. Let me work, please. Like Microsoft thinks that them updating Windows with things that I don't care about and probably will make my computer work worse and make it slower is more important than me getting work done and delivering value to the people. I think Microsoft is owned by Vladimir Putin at this point. Anyway, yeah, so we're going to see what this actually does. But the goal is just to have a simple function that diverges. And what do I mean by diverges? It means that these things, these sequences, if they start running together, they find separate places to go. And what I'm going to do right now is just step through it by hand and see how separate they are. And then we'll write some code that actually takes statistics on this. That's where I want to go with this eventually. All right. So let's use the numbers and letters in a different way than we were. So I'm going to say there's this array of stuff we're going to insert that's 1, 2, 3, 4, 5, 6, 7, right? These are all going to collide with each other. And we're going to have A, B, C, D, E, F, G. Those are all going to collide with 1. Oh, shit. Actually, no. These are all going to be neighboring. Okay, right. Because if you collide on... Okay. This makes me realize something about this probe increment function, right? Maybe you should add the actual hash mod something, the original hash. Because if things have different slots but map to the same hash, then this probing strategy that I put in is never going to make those diverge, right? But if you add some element from the original hash, then things with different hashes but that map to the same slot have a chance of diverging, right? Which is good. But after we collect some stats, we could maybe then change that strategy and show that the stats improve, right? That's what you said? Okay, good. Good on you. Good on you. Yeah, you literally just typed that while I was starting to say it. Okay. Right now, I'm in my now empty San Francisco apartment because I fled to a better place to live. But the one place that still has a desk that I could put things on is in what is now the machine room that has 3 other servers in it, and it gets warm in here. So I opened the door and I turned on the air conditioning, and we'll see what happens. Okay, anyway, so let's just see what happens under this strategy if one is going to land here, and A is going to land here, but we're not going to insert it till later, right? And we're just going to see. So we're going to put 2 here. So 2 collides, so we go 1, right? 3 collides, we go 1, that collides, so we go 2. It's going to be confusing saying numbers and then saying numbers for the increments, but it is what it is. Okay, 4, 1, 2, 3. And you can sort of see the patterns, so we don't have to go back and trace through all this. These are all going to collide with each other every time, right? Pretend like they have the same hash. And actually, this is kind of bad, so we can, it looks like we can improve the hash table substantially by not doing that, right? Okay, so anyway, we go 5, we skip 4, and we go 6, oops, 6, we skip 5, and we go 7. All right, this is how our entries land with this probing strategy, right? Now, okay, actually, let's show the difference, right? That's the new strategy. The old naive strat, which is the first one I shipped to the people, whoops, would have looked as follows, right? It would have gone 3, 4, 5, 6, 7. And now actually though, even though this looks worse so far, this one was actually a little bit slower because we had to add to an integer and we had to cover more memory, right? This one is actually faster because it does the same number of operations a little bit more cheaply. But then the problem comes in, now we're going to collide on this slot with this A, B, C, D, E, F, G, right? And in the old strategy, we would go A, B, C, D, E, F, G. It would be like n squared in a very bad way, right? So A, right, I said it's O of n before, but it's O of n search per entry that you add, and there's n entries, right? So it's n squared. B, C, whoops, D, E, F, G, and as we said, this is very bad. Now imagine you add a new thing here. It just goes through all this, right? Okay, so here, if we try to add A here, we go 1 over, so it goes here. Already, that's pretty good because we didn't go through 8 things, right? Now we try to add B here, we go here, and then we go 2, boom, right? We try to add B here, we go here, we go 2, full, so we go 1, 2, 3, C, right? And you see the pattern, we can go 1, 2, 3, 4, D, 1, 2, 3, 4, wait, yeah, 1, 2, 3. I got confused about whether I'm skipping 3 or going on the third. So here we're skipping, so we're skipping 1, skipping 2. I mean, it's the same, it's just off by 1, right? 3, skipping 4, E, skipping 5, F, and then skipping 6 for G. Okay. So you can see that's a lot better. Like, in the sense that well, a lot better. It's still not great because A, B, C, D, E, F, G keep colliding with each other. But these two runs no longer, okay, the 1, 2, 3s and the ABCs don't collide with each other anymore under this probing strategy, right? It's like only the ABCs internally collide and only the 1, 2, 3s internally collide, all right? So that just, you know, that's a lot better. However, we would like the ABCs to not collide with each other and the 1, 2, 3s to not collide with each other unless it's a genuine input hash. If the user gives you the same hash for 2 things, there's not a lot you're going to do, right? So, but if it's just 2 hashes that map to the same slot, we can actually improve on the strategy that's there right now. But I don't just want to type code that I think will improve on it, right? I want to get some metrics and then see with my eyes the metrics improve when we make the change, right? This seems like it's going to just build lots of small runs everywhere, but no. Like, well, as you fill up a table, you're going to build lots of small runs everywhere. Like, look, our load factor is going to be 70%, right? So there's only going to be 30% free slots in the table at the end. So you're going to have lots of small runs, right? The point is to make them as inexpensive as you can for these pathological situations that come up, right? The issue is still there if you incremented by primes instead of consecutive numbers. Yeah, so it doesn't matter if I pick primes or anything for this A, B, C, D, E, F, G collision that we have right now, because if I don't include some ingredient of their original hash, then I've thrown away all the information that differentiates these anyway. If I just map to the slot and then say that's the identity of this thing, now we'll do the search, then we threw away anything else that we could even use in principle to differentiate between these guys, right? We don't want to do that. We want to keep information that lets us tell them apart. And so I think maybe the best thing to do is instead, okay, here's one thing we could do naively, is just, okay, the simplest thing you would think of is like, oh, just add the entry mod the table size and wrap around the table. But that won't help you because you already landed on this slot because that's what the entry mod the table size is. So you're using the same thing that is already equal for all these guys. That is not going to help you. But if you mod by something else, like let's just say some small prime number that's relatively prime to your table size, and not bigger than your table size, right? Like 27 or something, that'll probably reduce these collisions by a factor of 27, but that's a constant factor. And so if you have a really large table, you'll still get the same problem, just 1/27th of the magnitude, right? And so maybe you want to mod by primes that get bigger as the table size gets bigger. I mean, okay, well, here's one. Here's an interesting thing, right? So the table sizes for this hash table grow as a power of 2, right? And I think we let people specify the original table size. So it's not necessarily always power of 2, but it probably usually is. And if you take table size minus 1, that's relatively primed table size for all powers of 2, right? Because powers of 2 only have factors of 2 in them, right? Power of 2 minus 1 is an odd number, which means it has no factors of 2. So regardless of what the other factors are, those two things are relatively prime. The question is just what happens if people put in a different funky table size. And I guess the answer is once we've, I don't know, we need to think about that. Probing strategy and table size will have to be chosen such that cycles don't occur easily. Yes, okay, so here's the thing. Yes, so the thing that you need to think about that I forgot to say with the probing strategy is it needs to be guaranteed to visit an empty slot eventually, or else you will infinite loop, right? Like, there's a bug that you could have where you just keep hitting filled slots forever, and you need to somehow pick a strategy that avoids that. Now, I'm pretty sure that incrementing by 1 every time is such a strategy. I believe. And I don't remember where I read that, but I'm pretty sure Knuth proves that or somebody. If that's wrong, let me know. But yes, there is a danger there that you infinite loop in a bad way. Yeah, right. That's a good point. The Mersenne primes are power of 2 minus 1, and they're primed to everything, right? They're primed to all other integers except 1. Well, positive integers. And themselves. But that's a stronger guarantee than we need, right? We just want to mod these input hashes by something that will make them give us a different result than modding them by the hash table size did. And you can probably I'm actually not sure about this. I was about to make an assertion, and now I need to think about it. So if the table size is 16, and you have some numbers that mod 16 all to the same slot, right? Then they also mod 8 to the same slot, right? That's the problem. I'm visualizing that in my head, and it sure seems right, because to mod 8 by the same slot, you just subtract 8 if it's greater than 8, and they all map to the same thing, right? And 8 is a factor of 16, right? Is that true, though? Because the thing I'm visualizing in my head is like after you have the collision, and I think it's before you have the collision, but I kind of feel in my heart like that's true, right? And I kind of feel in my heart like if the new mod that you're going to do is relatively prime to the table size, then you'll get different results. That's something we can test in code pretty easily as well. On your implementation of probing hash table, you hit the times collision, limit the times that collision could happen. After X collisions, the hash grows. I see. I mean, that makes sense. Like, that makes sense if you expect to be very unlucky or expect to have a bad hash function. I've never really considered that as a general strategy for a table, though. I wonder if that actually improves performance in the general case. I mean, the problem is that growing the table is very expensive, right? So growing the table is probably slower than having a lot of collisions, almost certainly. So really the question then is having a lot of collisions a big sign that you're going to have a lot more collisions a lot of times, in which case it's better to grow the table, right? I don't know. Yeah, it all depends. It all depends on your use case and stuff. All right, let me grab a snack real fast, and then we will just start putting some profiling code into the hash table. Like, I think what I want to do, I'm going to start out writing just a little user program that uses the hash table module and runs some benchmarks or statistics. And we're going to look at the statistics. And then maybe we'll turn that into an official example in the hash table module, because one of the things that's very important about programming, okay, the biggest problem in programming today, easily the biggest problem, is that knowledge is not being communicated. Various kinds of knowledge, right? There's specific knowledge that somebody wrote this specific code and they knew some things about it, and then they moved off the project or they died or something like that, and now you come along and want to expand that and maintain it or whatever, and you don't know these things, right? That is a big source of loss in software development, because now your work is going to be slower and less good because you don't know the things, right? Ideally, you should know all the things that the previous guy knew and be able to build on them and be better than he was, but that very often doesn't happen, right? Now, the second kind of knowledge that we don't communicate effectively is this tacit knowledge about how stuff works generally and what is a good idea to do and what isn't, right? So for example, guys, I'm 50 years old. I mean, I'm really 20, but I'm 50, right? So I didn't know this thing about hash tables, and I've used hash tables a bunch of times. And part of the problem is, if you go read about like, what should I do in a hash table, a lot of what you see is BS, right? And if you go take, in computer class, I honestly don't remember if we covered this stuff about hash tables in computer school. Uh, but we probably covered a lot of stuff about hash tables, most of which was irrelevant, right? I remember we also did like red-black trees, and we did like 17 kinds of trees, and I don't care about most of them, right? And so, and I was also told that programming those trees in Scheme was the best thing in the universe, right? So like, we're not very good as a whole at like figuring out which knowledge really is important and good versus which knowledge is like whatever, right? I mean, it's a mess. You learn this in computer science: linear versus quadratic probing, internal versus external chaining. I mean, yeah. I mean, I probably learned about different probings, but I'm not sure that I ever understood this. You know what? I actually think I never took this class, so I probably learned hash tables myself. Anyway, someone says computer school today ends at table.add thing. Yeah. Okay. Well, I'm glad this is still in school for some people. I think I think this would have been Professor Hilfinger's class at Berkeley, and I never took that one somehow. I also didn't complete the degree, but if I had, I would have done it without taking that class anyway. So I don't know. This is very missable in computer school. You didn't do any profiling. Wow, okay. We did profiling, but it was like fake profiling, where you like pretend that you measured good performance. It's a very different thing from real profiling. Like, I didn't know how to do real profiling until I was in the game industry for like 10 years. I didn't figure it out. Like, that's another one of these pieces of tacit knowledge that gets lost, because people go to profile, they think they're doing real performance analysis, but they're really doing cargo cult performance analysis. And I'm not saying that to be mean, because I also did cargo cult performance analysis for my first 10 years in the games industry. Like, learning what real performance analysis looks like and feels like is a thing that you have to learn. All right, back in a second. How do you pretend to profile something? You do what it says on the internet about how to profile your code. I have literally no civilized cups or anything in this apartment, but I do have like a thermos kind of a thing. And I have 2 flavors of sun chips and pistachios and licorice, so we're all good. This is all we need to survive. All right. We're going for the good flavor sun chips. How do I stay 20 while eating all that junk food? Have you seen what teenagers eat? This is like how to be a teenager. What are you talking about? You count the number of CPU files of functions with RDTSC. Are you cargo culting? It depends what you do after that. It depends. How do you know when something is pretty fast? someone saying, I found that lectures in school are so boring that you just decide to be autonomous until you actually need to learn the thing for your side project and then realize that you took it. That's basically how it was for me. So maybe that's why I don't know these things. Who knows? But I'm happy I know them now. Okay, we're going to make a program parameter for profiling. It's weird because I added this module parameters directive with 2 parameter lists, and I almost always use the program parameters. But for profiling kind of stuff, I think that's what makes the most sense. Anyway, I could make them. In this case, it's not really profiling because we're not going to count time right now. We're going to count collisions. You know what? I'm going to put it here. All right. So and the question is, should we count reprobes separately? Like you could take, you know, centroid invariance of these numbers and stuff. I'm not going to get that carried away right now. Like you could say, what's my average number of probes per insertion and what's the variance of all that? And I don't want to get too crazy about that just because, like right now, I also want to keep the code simple and readable for people. So when it comes to this profiling thing or counting collisions, I just want it to be really simple. Like I don't feel too bad about that, okay? But we need to make oh, whoops. If count collisions, then we have, we're going to make it an S64, because why not? Okay. Now this is not the only place, wait. Okay, so there's sort of 2 different things because there's add collisions and like search collisions, like how many times do we look for something when we're searching? And those are like 2 different things, I guess. Let's do this. Okay. So those are add collisions. And when we find, we're going to say find collisions for here. And there. Oh, actually, no. This is gross. So like if it's if it's the same hash, we count a collision here or there if it's a different hash. That's kind of gross. I don't like. This is a little bit of a weird function. Yeah, okay. We're just going to do that. See, I already don't like what this is doing to the understandability of this code, but it is what it is. For removes, we're not going to take any statistics on that. Okay. Here's the thing. When we resize a table, what should we do about this collision accounting? I'm inclined to say nothing. Because I'm kind of only going to use this with a benchmark where I know what the table size is, and so either I add fewer entries than that or not, right? So, meh. All right. Okay, so I'm gonna file this away. Just to give myself a small file called A in the classic C method. Okay, so we get a table, and we're going to go module parameters here. So we're going to say true, right? Because oh, this is hash table. I call this struct table. That's a little bit weird. All right, table is a table. What are the parameters to table? Key type, value type, hash function, compare function, which are optional, and load factor, which is optional. Okay, what do we want? I could make it a string table. I could just make it an integer table and pick random numbers. Module params need to support name parameters. They do. Who the fuck do you think you're dealing with here? Of course they do. Okay. Yeah, I just decided not to use it there because I was spacing on what the name of the variable was. If you want to, it is more self-documenting to do this. It's true. All right. So what kind of table? Like, maybe it should be a string table and we could just have a big text, right? And the thing is, we would want a very long text because we want to benchmark things for large table sizes, right? So we could do that. Or we could just pick integers. The thing about integers is they're less exciting. Like you don't usually store integers in a table very much. You usually store other kinds of data, right? So that's why I'm just a little bit torn here for a second. Like, do I do a big example that has like a book in it and we pick every line of the book? Like I can get, like how many lines? All right, we could do this, for example. This isn't the full text. Come on, guys. I just even want to know how many lines it is. I don't want a PDF. I want it in a text file. Plain text. Here we go. Here we go. $11,000 lines. That's not even that many lines. Are you kidding me? 11,000 lines. New Testament? How long is the New Testament? The Chaos by Gerard Knowles Trent. There is a Shakespeare.text. Let's see. Oh, it took the browser a little longer. That's 50,000 lines. Guys, these are kid stuff. We need like the list of all laws that you're expected to comply with as an American in the year 2020 or something really long like that. Like 50,000 lines is just paste that 50 times. But then we're going to get collisions in the data, and we don't really want that. You know what? We're going to start with integers. We're just going to store them as the key and the value. It's going to be awesome. All right. Let's just make 1,000 things. So I'm going to size the table. To like do we want to fill the table up to the load factor? All right. We're going to have some get num elements that does something, right? So we're going to go, it takes some table, whoops, and we want to make the table big enough that the load factor times the table size is greater than or equal to n, right? Um, so yeah, to add, right? Okay, so we kind of want to divide, right? We divide by the load factor, and we multiply by 100, because the load factor is an integer in percent, so it's like between 1 and 100 or whatever. Width is to add times 100 divided by table.load factor percent plus 1 to get rid of junks, right? I think that's right. Load factor, we're just going to print the load factor, and how much we're going to add. We're just going to sanity check this number real fast, because we don't actually want the table to expand, right? So all right, we're going to return that. All right. Cool. Why am I running the debug compiler? Because I was working on the compiler. We're going to run release. Okay, so 1429, right? Times a 70% load factor is 1000.3. So there we go. And we can also check that the table did not expand, right? At the end, we can say, oh, the number of entries is still the same, or the allocated is still the same, right? Okay. When people say "hey, blow," are they from China? Like, do they think that that's how people address each other when they speak English? Because it happens a lot. Anyway, hello. How's it going? Um, so this is a good step. We have a valid thing. We have a valid table size. It's all good. Actually, I guess I rounded up to the next power of 2. Oh. I mean, I guess that's good. So this table is a power of 2 size at all times, which actually might be inconvenient for general purpose use. The reason I do that is because when you want to wrap around the table, you can bit mask instead of mod, and that's faster. However, it's like on modern CPUs, that's maybe not your biggest problem unless you have a lot of collisions, which we're trying to avoid. And there are other things you could do. Like, I think if you're like power of 2 plus another power of 2, that gives you a lot more flexibility, and there are cheaper ways to wrap or something. Or also, instead of modding, you could do an if and a subtract. Of course, that gives you a branch to predict that you probably mispredict a lot. I don't know. We could think about that later on. Anyway, for now, we're power 2 table. All right. Now, so that's interesting, though. I should do this in reverse order because I want to add up to the thing that's going to make it expand. So let's do this in reverse. Let's just say n is get num to add from table, right? Actually, need both these steps because I want like, oh, about this many elements because we're going to keep growing. Like we want to make a test. It's so weird because the way I conceptualized this was, oh, I want to try for a small table and then a bigger table and a bigger table and a bigger table and see how many collisions we get, right? But like because it's power of 2, we're not controlling the table size super tightly. So it's like I'm going to start out and say I want a table about this big. It's going to give me back the power of 2. Uh-oh. Guys, I just kicked the server here and it's giving me an alert now and it's beeping. I might have to shut it down to make it shut up. This is what happens if you, on the RAID server, you open one of the hard drives and jiggle it. Don't do that. We're gonna take a short break in the stream, and I'm gonna like log into it. In high security mode here. Because I could just hit the power switch, but it's probably better to actually reboot it. No disk station found within LAN. Come on, guys. No, it wasn't a power surge. I literally kicked one of the drive things and loosened the drive while it was running. He was angry at me. It claims it's on the LAN. But we're not finding it. Let me download their thing. What's the model on? Dude, they don't put the model on the front. Just give me your frickin' thing. God. Like all these marketing people, there's this thing where they pretend that to download the program that you need to select a specific thing, but really it's like the marketing people. NVIDIA does this too. They want to collect stats, and like when you have an emergency happening, it just makes me hate them, right? Oh, you can't hear me? Yeah, you can. Yeah, you can. What are you talking about? Wait, why is it? Oh, I downloaded the wrong file. All right, this is a really entertaining diversion. That's what I get for working in the machine room. Oh no, I just closed the page. Let's go back to the page. Desktop, oh, I have to click on desktop utilities. There we go. Windows. There we go. English. Do you speak it? Do you want to install this device software? Yes. All right. So now, here we go. It is not finding servers, maybe? It might be that I'm on Wi-Fi as well. Like, it mightn't be that you need to be plugged into the LAN to find people on the LAN. Or maybe I should just hit the power button. What do you guys think? Grab the local IP from the router's admin pages. I could do that. Let's see. I don't remember what the router address is now, so I get to guess. Oh, wait. I hope you guys like the beeping. Aha! Device details. IP address. I have the IP address. Aha! It is up. Hope I remember my password. Password is invalid. All right. Password is invalid. Now I really don't know. Let's see. Okay, let's try. Oh, wait, I have the password in my web browser. That's good. Oh, it's up. It is up, but it is giving me an exclamation point. Critical issues have occurred to storage pool 1. Critical. Insufficient number of drives. Critical. 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 All right. It's not giving me much action, so do I just try rebooting and see if it decides? Like, I'd rather just have it. I'd rather just have it. Like recontact the drive. I don't know. I don't know what to do except it's not really giving me anything intelligent to try. So we're just going to reboot and just see if that's a disaster. But we're going to soft reboot instead of hard reboot because maybe that's better. It says, please go to Storage Manager for more information. Yeah, but you're not telling me the more information. Like, I can't. Oh, read this article to repair a degraded storage pool. Okay. Storage Manager, Storage, select the pool in degraded status. Where is Storage Manager? Now, Storage Manager, Storage Pool 1. Okay. Click the upper right icon and select Repair. Repair. There's one drive. Yeah. Yeah, I want you to start using that drive again. Like, I can't get it to wake up the drive. Like, guys. Just re-talk to the drive. Okay, I'm just going to reboot. Maybe rebooting will make it re-talk to the drive. I don't know. How do I reboot this thing? Restart. All right. Maybe it'll magically stop beeping. Okay, it has stopped beeping due to shutting down. The question is, after restarting, will it once again begin beeping? And we don't know the answer to that. Yeah, the lesson is don't absent-mindedly kick the network storage device while you're thinking about hash tables, I think is the lesson. See, in all the discussion that we were having about things to worry about in hash tables, like, is your hash function good? What's your reprobe strategy? Are things stored in a linked list or consecutively in the table, right? In all that, we didn't think about kicking the network storage device. It says restarting, and it's just still like, you know, it's doing like one of those progress bars. It's like a linear, I'll show you guys. Actually, no, I don't want, there's a small chance of sensitive information, but it's got one of those linear progress bars, and then it takes like 4 seconds to fill up, and then it just starts over. It's just going and going and going and going and going. All right, well, let's not worry about it for a while. How's everybody doing? I think I need to open the case and reseat the drives. Well, I'm certainly not going to do that till it shuts down. I mean, I did sort of make sure the drive was plugged in and stuff while it was running, but it didn't like that. And I don't want to take the drive out while it's shutting down, because it might be writing data or something, even though it doesn't appear to be. Like, none of the drive lights are flashing, so I don't know why it's taking so long to shut down. Sag. Deallocating all the memory. Maybe, you never know. Okay. So I think Twitch lets me easily export multiple things now. So we're just going to go back to unplug it. Last time I just unplugged it while it was shutting down, it died and I had to buy a new one. So we're not going to do that. We'll go back out of high security mode and let's talk about hash tables some more. So, oh, it's starting up again. Literally right when I did that. Hold on. The lights are flashing all over the place. We're full blinking lights now. Like I can just hear the drives. I can hear them. I can hear them. All right, dude. So hash tables. So like I was saying, we're sort of letting the table pick the nearest power of 2 size, and then we'll do the inverse. We'll say to add, this is kind of silly, but I'm not really sure what to do. All right. Right, so we're going to say we're going to round down, right? So that's easy, right? So we're going to say to add is, oh God, guys. All right, I'm going to try reseating that specific drive. I'm going to shut it all the way down. We're going to reseat that specific drive. And yeah. At least now I know the password and stuff, so all this will go faster. I mean, I can always go out today and buy a new drive as well. I actually have a spare drive that was being used as cache that I could plug in if this doesn't work, but all right, anyway, we're going to shut all the way down. The drive might be reading fine now. I mean, it's got a red LED on that specific drive and green on the rest, which is what it had when I kicked it. So, like, I don't know what that means, but we'll see. Okay. So, oh. Wait. Allocated times load factor divided by 100, right? Okay. So we're going to go so that tells us how many things we're actually going to add to roughly achieve the load factor of the table after it's memory sized. Oh, yeah. Load factor percent. All right. Yes, this is not uppercase. All right. So we're going to add 1433 to it. That's great. Actually, that 1429 number was fine. Am I dumb? Am I dumb? Right, yeah, we're just computing the same thing here, but with different rounding. So that one's actually fine. Wait, did we just get lucky there? That those numbers are so close? Like, what if I do this? No, it's not overnight, though. Yeah, no, we got lucky. Okay. That wasn't different rounding. That was literally, we picked one that happened to land within 3. Low probability event. All right. Cool. Is it right that my console color stayed blue? This is just a stupid thing about emitting color codes to the console. Like, I think that just happens sometimes. Like, if the program crashes before you set it back to normal, it just stays that way. It's stupid, dude. It's like one of the many things that is so dumb about the way everything works. All right. The RAID was using physical hard drives because we set it up a few years ago when that made sense cost-wise. These days, I am not really sure that it makes sense. Like, maybe we should make a new one that is all just... all right. I'm pulling out... Oh, look, there's some dust on it. 4.0 terabyte Western Digital. I bet this isn't going to matter. I'm going to plug it back in, and it's still going to be unhappy with me, right? That's probably what happens here. And then, I don't know, maybe I just made myself a giant administration task, and I'm supposed to get on a plane tonight. Let's see. Anything else I should do besides pulling it all the way out? Blowing on the connectors? Yeah. Pretty sure it's intentional to be able to do it via scripts. Yes, but that is dumb. It is dumb. It shouldn't work that way. Like, you shouldn't be able to permanently set the color by doing the same thing that you do to temporarily set the color. Like, if that was a thing that you put in to be able to do it via scripts, it should require a permanent set flag, right? You know what I'm saying? All right, let's just see what happens. I don't think that's going to fix anything, but we'll find out. Anyway, it will probably start beeping in about a minute. So, we can explain what's all happening here later, but now we're going to go for 1 to n. We're going to go random get, right? We're going to print the table at the end. It's not going to matter. It's not going to show us the elements because a lot of them are uninitialized, but it'll show like that we added this many things, right? So I'm going to go table add, table number, right? Yeah, key value. Yes. So we're just going to add this many things. And then we'll print the collisions that we counted. Okay. We didn't ever find anything in the table. Add collisions, 3,285 in 1,000 adds. That's quite a lot. It's quite a lot. I mean, I don't know. I don't know what you typically expect in a very high-performing hash table, but I already print the collisions to print table. That's true. It's right there. It's literally right there on the screen already. So, okay, one thing that I want to do. Oh, I forgot to mention. All right, we need to figure out a way for me to know later on where to go when editing the thing. Let's see how far we are into the stream. I am not authorized to use the service. Yeah, because we shut down. We are 1 hour 50 approximately. Okay, because we got to resume the explanation. This is the thing that I want to test for. Hold on. Oh, I knew it. I knew it. Okay, before we do the rest of the explanation that we will put on YouTube, let me try to do something. I have one other drive that was here as a cache. Like, maybe I just completely killed that freaking drive. Maybe I shorted it by kicking it. Anyway, what I could try plugging in this drive that we have. I don't know how big it is. but I could like dedicate it as a cache. And we'll see what happens. Maybe I just have to buy a hard drive today. Wait! Oh, weird. Okay. The diagram of the drives. Wait, the number 10 is not the one that I kicked. I'm so confused. Maybe this doesn't... I'm really confused. Anyway. Drive 10 unverified. These all say unverified. I don't know what that means. But it's detecting it. It knows it's there. Okay, the Samsung that I just plugged in is okay. Like, I don't know if it's actually still having a problem with this drive or if it's like just remembering that it has a problem every time I start it up. The requirement drive status is not met. It's okay. How do I change the drive status? Drive 10. It like doesn't give me any options of what to do with drive 10. Like, what do you want me to do? Give me some action. Secure erase. No. Health info. Smart test. Okay. Anyway. Why is it not allocated to storage pool 1? Why? Like, okay, I sort of see what happened. It's got some data structure of who's in storage pool 1. And, like, when I kicked the drive, it, like, removed it from the pool. It's just not in the list of drives that are in the pool. I don't see how to put the drive back in the pool. Synology server, add drive to pool. Storage pool, action dropped. It says there's an action drop down on the storage pool. I do not see such a thing. There's add drive, but it's grayed out. Like, why do computers suck this bad? Like, just tell me, like... Like, I'm just trying to do something. and it won't help me at all. Even though billions, not billions of dollars, but many, many tens of millions of dollars at least have been spent developing this product, and like, it's got all these fucking windows of things, and like, I have no idea what to do. Can I SSH into it? I'm logged into it right now. That's not a problem. I've got a whole window system full of windows and drop downs and all this stuff. It's like, I can't. This drive is not assigned to a storage pool anymore, and it won't give me an option to assign it to that storage pool. The requirement drive status is not met. Health status warning. Do I have to suppress the warning? Let's try that. I saw something about suppressing warnings. That sounds great, right? How do I get back there? It's so confusing. There's like so many menus that like don't do anything. Health info. And like each of them has 3 things. Overview. Modify suppress drive warning. Okay. Drive 10. So if I go back here and say like, it's so confusing. There's so many menus that do the same thing, but they don't all do the same thing. Like now I'm just trying to get back to the modified storage pool to try and add the drive. I can't even find where that was again. It's so confusing. Repair. Oh, it's giving me it's giving me a separate thing. It's going to erase the data. Okay, no, you know what? Here's what we're going to do. I'm going to go to the, I'm going to shut this down for now. I have to go to a doctor's appointment later today, which is the whole reason I'm in town today. And we're just going to buy 2 new drives because it's going to erase that one anyway. We're going to buy 2 new drives and slap them in there. And we'll see how it goes. All right. So we're not going to worry about that anymore for now. Hope the data on the drive is backed up. It might be. It might be backed up. Okay. Anyway, to get back to the hash tables, let me write down what time it is and turn on the screen again. To get back to the hash tables, let's talk about this birthday paradox thing. How far are we in the stream? 2 hours. Okay, let's talk about the birthday problem, paradox situation. The birthday situation is a little bit odd in more than one way. And part of what I wanted to do today was do this experiment to try to understand this better. All right? It is not only the case that, given a certain table size, the size that you get before you expect a collision, or the number of insertions that you get before you expect a collision, is pretty small, and therefore you generally get more collisions than you might naively think. Okay, that is true. But also, it sure looks to me, looking at the math, like you get more collisions as the table size gets bigger, even for a constant load factor. Because down here, they sort of give you these functions of these are the numbers that are in this graph up here, I guess. But what we care about now, they have these approximations for if you want to, there's a section here that says, okay, arbitrary number of days. If you're following along at home, you can go to Wikipedia birthday problem and arbitrary number of days. And so they give you an equation, or they derive an equation, and the equation is more complicated than you would think if you want to get it exactly right. It's like, right? It has a bunch of terms, but there's an approximation. Like if you just basically want to know, right? Then you can use this ceiling of square root of 2d ln 2, and I graphed that. You don't even need the ceiling. The ceiling is just like give me an integer result back, right? But here, so square root of 2x ln 2 is, for a given table size, which I've graphed along the x-axis, I go up to 100,000. You might have a table much bigger than 100,000, right? It's a modern computer. On the y-axis is how many insertions do you need to get a 50% chance of a collision, I think is what that equation is. Right? Something like that. So the 365-day birthday is like way down here on the left, right? And as your table size grows, you'll notice this is under the y equals x axis, like way under, right? Like the y and the x are not even at the same scale. If the y went up to 100,000, this would be way under, right? And so what you might naively expect is if I double the table size, then I double the number of, well, if I double everything, right? You might expect if I double the size of the table and I double the number of things I'm inserting into the table, but I keep the load factor the same, then I would expect about double the number of collisions because it's the same density, but like double the number of elements, right? This equation appears to say no, you'll get more collisions in a double table size than in a non-double table size, right? And then as the table gets bigger, that gets worse. That's unintuitive, I think. And so I kind of just wanted to test that with code. A way you can think about it a little bit, about why that might happen, or my best explanation to myself about why it might happen, is because you're not just scaling up the whole problem, right? Scaling up the whole problem would mean, okay, we double the table size, and we either keep the same number of entries before and they're all like too wide, or we double the number of entries but we somehow force them all to be next to each other so that you fill 2 slots at a time, and then you would get the same number of collisions as in the smaller table size. But here that's not true, right? It's like whatever was 1 slot in the old table becomes 2 slots in the new table, and they each are free to move around and collide with anyone, and I guess that makes more birthday collisions or something. And so kind of what I wanted to just do was see that happen in an actual program and go like, whoa, right? Now, the thing is The thing that I'm not sure about is we already mentioned that my reprobe strategy is still suboptimal and generates some collisions, right? It's not great. And again, we can try fixing that and observing that. But is that going to change this outcome dramatically as well? Is the way in which the reprobe strategy is not good also dependent on table size, or is it orthogonal to table size? I don't know. I don't know, man. Okay, let's just factor this thing that we did into a function, and then we'll just, call it for some different table sizes. And you know what? This whole thing here about starting with an n, let's not even do that, right? Let's just do a table of a given table size. And we'll just make those power of 2, because then we're not juggling so many numbers, right? So we're going to get rid of this. We're just going to say table size 1024. And, oh, shoot, I even went to the wrong number here, by the way. That's supposed to be 2add, not our original n. That might explain why there were so many collisions. Yeah. No. This is just this. We're keeping it simple. Okay. Yeah, I deleted the wrong things, guys. Yeah, don't worry about it. Don't worry about it. It's all good. Okay. Yeah, we still got a lot of collisions. All right. So 716 items in the table, 1,024 slots allocated, right? 716 of them filled. I don't know why these are separate numbers. Oh, these are separate numbers because with this table, if you remove items from it, it leaves a poop there and the slot stays filled until you resize. And the reason for that is because when you're doing these reprobe chains, if you break a reprobe chain and claim that that slot is empty, then someone trying to find an item in it may stop looking before it finds the item, right? If you make a hole. So you could make a hole that is empty only for the purposes of adding. I'm not actually sure if I do that right now. So let me just see. That's an interesting question. If I let you add back into those holes or not. I should differentiate between collisions and number of reprobings? Maybe. Yeah, maybe. For now, I'm just interested in general in number go up. And then we can get more sophisticated about that later. So I'm going to make a function called do table size. Right? We'll just say int, whatever. Whatever, man. And then we're going to do this. And I might not print the whole table later, which is why I'm just printing specific things. All right. We literally put everything there. Okay, so do table size 512. Actually, for 110, I'm going to say table size. It's not much point in having like a really tiny hash table, right? So do table size equals 2, right? So 2 to the 10th is 1,024. So we're going to have a 512K element table at the end. All right, let's just see what happens there. Okay. I guess it's half of 512K. Oh, because we only multiply by the last 2 at the end before we do the last table. That's why it's half of 512K. Okay, so great. Um, you'll notice here that here the number of collisions, we could actually print out this ratio, is like 7 times the table size, right? It's almost 10 times the number of items in the table, right? This is a 7-digit number. This is a 6-digit number. Here, the number of collisions is also bigger, but it's like 5 times. What about in the middle? This is more than 5 times. So it appears that we have a lot of collisions, but it does get worse as the table size goes up. Let's go up by even more. And let's actually we're just going to make a float. What's it called? Table.count. All right. Oh, it's starting to slow down as we get chunky there. Okay. 11, 10, 10, 9, 9, 9, 8, 8, 7, 7. Yes. So you can see that this grows with table size. Astonishingly. Now, some of this might be an artifact of our reprobe, but I don't think so, because the Wikipedia, Jimmy Wales, we gave Jimmy Wales all the money, and Jimmy says it will get worse with table size, according to this graph that also Stephen Wolfram says. All right? And this is not, like this graph goes down as you go up, which seems good, but it's bad because this is number of entries you need for a collision. Goes down relative to table size as table size goes up, which to me is an astonishing fact. Okay? That is not something that I had clear in my mind. This is something, if you're a C++ person and you like std : hash map or whatever, you should just be able to run the same experiment yourself because it shouldn't depend on the implementation, right? If this is actual hash science, it only depends on size of the table. Who knows? I mean, maybe your table implementation has a mitigation strategy of some way, but actually, yeah, I don't know. You can run this experiment yourself. Is this also due to birthday problem? Yeah, that's what we just got done saying. You can replace a deleted entry with a tombstone to avoid breaking the chain. That is literally what I explained that I do. I just didn't say the word tombstone, so you didn't maybe get that that's what I was saying. Okay. Now, that's kind of interesting, right? Let's build a release build of that. See if it goes faster. A little bit. It still chonks along when it gets big because of all those collisions. Yeah, so it's more than, okay, so you expect to get slower as the table gets bigger because you have more elements, right? But we started with a factor of 4.25. We ended with a factor of 11, like almost 3 times as slow per element, like per capita of thing that we put in the table, right? That's a lot. That's a lot. Now again, maybe if we fix our reprobe strategy a little bit, we can do something here. The thing is, it involves doing a mod, and it probably involves doing a mod even before we know that we have a collision, which is kind of ass, but we have so many collisions. Like, look at this. We try inserting every entry 11 times. Oh, here's a fun experiment we could do. I can devolve, remember we have our probe increment, right? What if I just take this out for a second? Whoops, hold on. We want to take out the probe increment plus equals 1. What is this? Oh, remove. Yeah. So probe increment plus equals 1. So now we're going back to the strategy that I explained at the beginning is like real bad. And I kind of wonder, how long will it even take? Okay. So you can see, now we're at 20. We were at 11. Or were we at 11? We were at 11 before. Now we end at 20. So we're twice as slow. Pretty much the whole time we're twice as slow. So we went from 4 point something to 9. And we went from 11 to 20. So it's twice as good to do this linear probe. But we should probably be able to get twice as good again in terms of number of collisions, but we add a mod, which is maybe not great. Okay, let's verify that we're back at 11. Yeah. Okay, now this is much worse for memory locality, but hopefully a lot of the table is hot when you're using it. Let's just try. You know what? Okay, hold on. Let's make, I just want to take a second and make this output terser. So find collisions we're not using. We don't want to print the whole table. Let's just go, table size whatever. And that's, let's just say elements. How many elements did we add? And the table size. All right, so this is to add and table.allocated. All right. Add collisions is this. Collisions divided by elements. Let's say elements. No, entries. Entries is fine. Entry. We just want to use consistent terminology, right? So, okay. Since these numbers get big, let's do some other fun thing. So let's go context.print style.default format int digits per comma is 3, comma string is comma, right? Because we're printing big numbers and I want to be able to read the big numbers. And so let's take the comma out here because it just, if comma means a thing. All right, so there we go. That's much more readable. So we have 65 million collisions in our table size 8 million. 5 million entries, 6 million-ish. All right. So hopefully that all makes sense for everybody. So now for our reprobe strategy, I'm going to make a little inline function that we can tweak. And initially, it's not going to do anything. Here's what we're going to do. Whoops. Go back to hash table. Probe increment. We're going to say initial probe increment of hash. All right? We're going to replace all these with that. Every time we have that line, every time we have that line, every time we have that line. All right. What is initial probe increment? I don't have to, I'm sort of putting it right before the first use, C++ style. We don't have to do that, but whatever. Is hash a U32? Hash function returns U32. I don't know why I made the hash as U32. Honestly, maybe they should be 64-bit. I don't know. That's probably pretty easy to tweak because we don't, I mean, we store the hashes. That's probably why, actually. That's something we could think about later. We could think about making it a parameter to the hash table. It's just that that introduces more complication that people need to think about to understand the code. So, Okay. Literally not any different because this is just what we did. Okay, well, what if it's 2? What if we just start out a little bit better? Or a little bit more? It doesn't really make a difference, see? We're basically at 11. All right. Now, what if we say 1, okay, well, we didn't pass enough parameters. So we're going to pass the table in. We're going to say table, table dot what? Table dot, we're going to hope that the table is not 2 elements large. Hash mod table dot allocated -1, and we can explain this later if we keep it, right? All right. So we're going to replace this with table. What's our job? Tables. Okay, I goofed. Number signage mismatch. Is table dot allocated? Oh yeah. Okay. Just for the purposes of running this experiment, like the problem is these things are U32 and we want a U32, but what if the table is big, right? For now, we're just going to cast a U32, but we'll see. Oh my God, guys. Look how many not collisions that we have now for large tables. It still gets worse, but it's not that much worse. So we start at, actually it's very noisy. So like we start at 1.3, we go up to like 1.48 for some reason. And we go up to like 1.5. So it's growing, but very slowly. Like the amount of noise here makes it hard to see a trend if indeed there is one. Now, because we made this so much faster, we made it like 10 times faster, right? Because we eliminated all those collisions. So because we made it 10 times faster, we can go 3 more table sizes up easily. We'll do 4, right? So instead of 1 to 15, we'll go 1 to 19. And we'll see if we can observe a trend. All right, there we're starting to, probably starting to swap or something, I don't know. Just have very bad memory locality. Okay, now there's definitely a trend that you see starting to happen, right? Oh, we're up to 2 by the end. Which is also why it's taking so long, is like it starts at 1.4 and then goes to 2. So now the question is that somehow also a deficiency of our reprobe, or is that birthday problem? You know what I'm saying? I don't actually know. And then should I make a loop? Should I somehow, because doing that mod on every ad feels bad, man. Should I somehow complicate the code so that we only do the mod if we miss? I don't love that, but we could do it. Now the other thing is maybe I broke the hash table, right? Who knows? So one way we could check if we broke the hash table is build the game, because the game uses the hash table quite a bit. I mean, things loaded, assets loaded and stuff, right? So it's working. Like we're finding, like when we start up the game, we have a bunch of hash tables for like what are the texture maps, what are the meshes and all that. And then we look them up by name later. And if that were not working, the game would be very sad right now. So it appears to be working. Power of 2, shift and mask. No, because the whole problem is we need something that's relatively primed to the table size, and the table size is power of 2. Now, that said, if we're going to mod anyway, then maybe we don't need the table size to be power of 2, right? I'm getting really hungry. Anyway, though, let's run this again, and we'll watch it get real slow as we get big. Now, one thing we could do, like, if this is actual science, right, then as the table gets bigger, we could drop the load factor to compensate and get fewer collisions. The problem is that, well, that takes more memory, right? And you don't want to spend more memory as your table gets bigger, because big is when the memory really matters. Small, it doesn't matter so much, right? Fortunately for the game, our tables are pretty small. But you see this relatively marked peak here kind of goes up. Maybe this is like exponential, which would be scary. Because it's hanging out like 1.3, 1.4. It's got like a big bump here, which is weird. That could just be us getting unlucky. Maybe we should seed the random number generator with the time or something. I don't know. Anyway, though, as we get up here, it starts to get scary. Our 134 million entry hash table with 93 million elements in it. Does it really affect the performance of the game? It might. You know, like we have thousands of meshes and thousands of textures, right? And we might look them up quite a bit. Who knows? Clear the... I don't think typing clear will fix this, right? Oh, wait, did it? Oh, it did. I didn't think that would work. Dude, look, the text is blue. How great is that? Wait, it's blue again. Yeah, never mind. We have to exit the console with extreme prejudice. All right, we have to go. We're just going to kill this one. Wait, are they both blue now? They're both blue. They have both done the Tobias Funke methodology. So we're going to make a new one that is not blue. There we go. Look, it's not blue. Like, this is how bad computers are, guys. Okay. Now what? It's interesting, by the way. I was using a hash table for some stuff in the compiler, and it ended up being too slow, so I took it out. And I think I benchmarked the collisions, and it wasn't that bad, but maybe I didn't. I don't remember now. Like, it could have easily had this problem because it was a pretty big hash table. It was like, I don't know, a million things. I don't know, a lot of things. Hundreds of thousands. It was like one entry per node in your program. And internally to the compiler, we use a different hash table because it's C++, but we use our own. And it was modeled after this one, and it might have the same problem. Who knows? Does this test include deletions? No, this is just a very simple add elements to the table. And the reason is because I'm trying to observe a science element to it right now. We're not even necessarily trying to maximize the performance of the table, although we're a little bit doing that. We're just not being serious about it, right? We're like, oh, we don't want to be egregiously off. Which we were, by the way, because that probing method was not good. Try returning a random value for probing. Well, if we do that, we will break the hash table because you'll never be able to find the item. Right. Now, if we really just want to get these numbers, that's fine, but I'm going to have to comment it out. Like, I can't recompile the game with that in there, right? Because the game will break. But we could do that just for these numbers. I don't know why I put that in extra parentheses, but we ended around 2, right? So we'll just see if we end around 2. It looks like we're not. It looks like we're not going up, guys. Okay, this is interesting. That was actually a good experiment then. So this looks constant roughly. Which surprises me because Jimmy Wales told me that it would get worse as the table size goes up. But here it's really not. However, is that because picking random for reprobe is actually destroys something? I don't feel like it should, but there might be something subtle there. Or is it because I misunderstand something about maybe the probability of having any collision goes up, but the average number of collisions stays constant. Like that could be a thing. I don't quite understand, but that would be a thing. Seems 1 over, what seems 1 over load factor? I don't, you can't just type in context-free things into chat and expect me to understand. .46 is 1 over 0.70. That doesn't make sense though, because I think that's a coincidence. We can try it, but that would mean if the load factor goes down, your collisions would go up. Right? Like, look. So down here, when we instantiate, so when we make a table, load factor is one of the parameters, and we can just give a lower load factor in all our examples, right? So we could say this is 50 instead of 70, and we'll get a different number of collisions. Wait, we are getting more. now I am so confused, guys. What is even happening? How are we getting more collisions with a less occupied table? This is banana cakes. Is that a bug? Like, what's happening? This this random function, let's reset this for a little bit, because where are we? Having this be random is a little bit weird. So we'll keep that around for a second. And we'll go back to this. Which still, we may be able to do something better here anyway, right? But yeah, we get about the same answer. It'll probably go up at the end like the other one though, right? You set it to 25, do you get 4? I know, it's a little scary. Why? Like what? I don't get this. So either we have a really weird bug in the hash table, or we have a really weird bug in our user code that's printing this stuff out, which could invalidate everything we've done in our whole lives, right? How do we have more collisions with an emptier table? How does that even make sense? Is it that 50, okay, 50 might be special, guys. Load factor of 50 means we're generating a power of 2 number of entries. That shouldn't matter though. But like 50 is weird because we're multiplying a power of 2 by a half and getting another power of 2, which is sus, right? But it's not that sus. Let's try 33. Oh, guys, no. Guys, you know what it is. No, I was going to say maybe the table is resizing, but it shouldn't be. Let's assert that it's not resizing, and we could somehow put an assert in the table, but instead we're going to say old allocated is table.allocated, right? And then after we do all this, we're going to assert old allocated is equal to table.allocated, right? And then I don't know if I turn off asserts in release build. So we're going to do debug builds for a bit, again, just for avoidance of doubt. It's, oh. Wait, what? What? That, oh. See, yeah, there's nothing there till after you initialize the table, guys. Okay, great. So the table is not resizing. Wait, now we're getting a sensible. Do we have a release build bug? We might have a release build bug. Okay. This is what I would expect for a low load factor is you have the low number of collisions per entry, right? A lot of the time we don't collide. Let's go back up to 50. No, 50 is trash somehow. 40. 40 is way better. What? Although 40 is like a lot higher than 33. What about 45? We're approaching 1. 49. We're at 1. There's just got to be a bug. Maybe there's a bug in the math. Like maybe we're dividing wrong or something. We go from 1 to 2, guys. That's a frickin' bug. All right? Of some kind. Right? Because if you divide by something, like your integer rounding could come out different. I just don't know. Like, and then we're lower for 70. What is going on? What is going on? Look at that. At 51, we're at 1.08, which is consistent with what we were seeing at 45, 49. It is just literally at 50. We double. How does that make any sense at all? This is one of those bugs that when you wait, now it's 1. Did we recompile? Did I save? Oh wait, no, that's 51. Yeah, 51 gives us 1.0 whatever. 50 gives us 2. That's insane, guys. What is happening? 50 is UB. Yeah. The C++ specification says using the number 50 for a load factor is UB. Yeah, let's see if there's a singularity at 25. That's a good idea. Let's see. Not really. Although maybe it's just a lower singularity, right? Oh yeah, there is a singularity at 25. So 24 is really low. 26 is going to be really low. 25 is really high. How about 12.5? There's got to be some really dumb bug. And now I'm looking at this. This really is a quarter of the number of items, right? So it's not anything about resizing the table because we're asserting, if the assert's working. It's not that we're doing this wrong. So let's just check these numbers. 1048576, 4194304, right? So we're going to go to 24, and this should give us a slightly lower number here, same number here, because we're just multiplying down to get this one, right? Okay. Is this about 1/25 less than that? I think so, because it's about 45. Yeah. Yeah. And this is the same number. So that's what we expect, but it's dramatically fewer collisions. What is even happening, guys? Maybe the hash function, but the hash function is orthogonal to this. And if it were the hash function, then we should only get more collisions if we add more. But we're getting less if we add more things. What hash function am I using? I think I'm using like SDBM or something. It's nothing incredibly special, but it's like, you know, it's not y = x. This is really weird. This merits further investigation. Okay. How do we use load factor? We assert on it. We expand, but we've asserted that we don't expand, so this isn't happening. That's literally it. That's literally all there is in the entire file. So it's probably an artifact of the way my user code is doing something, right? Right? It's probably not the table. So we say allocated times load factor divided by 100. I mean, that gives us these results, and these are in line with what we expect. They're about a quarter of the table size. This is a mystery. This is a real gosh darn mystery. Like maybe there's something really kind of emergent, like maybe our reprobe strategy causes a lot of collisions in some exact case, but I don't see how that could be even, okay? Because I don't think the random that we're using seeds, and we took the random out of the hash table, so we should be getting the same numbers every run. Like, this is 649941. Let's just see if we get exactly the same. Yeah. So it's a deterministic random generation. Now I might think, oh, by rolling a different number of them, you get a pathological case, but it's happening exactly at 25 and 50. If table dot out, so you're asking about this. Here, this is like how much of the table is full, plus 1 because you want to round up, right? Times 100, right, is greater than or equal to allocated, the total size of the table, times load factor percent, right? And what is this? This is just doing a divide without doing the divide. So you can imagine, pull the 100 down here and make this over 100, right? So you're taking the allocated slots times 70 out of 100, or whatever your load factor is. And if we're greater than or equal to that, expand the table. Is it happening at 75? Good question. Maybe it's not powers of 2. I mean, 75 is a little weird because we start getting up into the territory where interesting. Now we're asserting that we expanded the frickin' table. Which shouldn't happen. So there is a bug here. Why did we expand? We added... Wait, why did we... The rounding up doesn't work for 512 and 75? You know what? I bet we got an equal to. I bet 384 is exactly... Here. 512, right, times 100 divided by 75. Wait. Wait, how do we get 384? Hold on. Hold on. That's... That's not even... If our load factor is 75, then why did our 2 add? What? How did we get this? How much is actually in the table also? Okay. Let's use slots filled. This is really weird. But maybe this tells us. Okay. Occupied 384. What? Why is that number so low? Oh no, because it's 384 out of 512, guys. Right. Right. I'm looking at the 1024, and that's why I'm confused. 384 out of 512. Oh yeah, somebody even said that. 0.75. Exactly. Okay, wait. So 512 times 100. Oh no. Sorry. 512 times 100 is this, right? And then divided by 75 should give us 384. Did I do that wrong before? Why does it give us 682? What is it? Hold on. 384. Okay. 512 times 0.75 equals 384, right? Right, we're not going insane. 512 times 0.75 is 384, okay? Which is 75 divided by 100. So 384, right, okay, 384 times 100 divided by 75 is 512. And that's what we're checking supposedly, right? So table.slotsfilled would be 384 times 100. So I just got confused when I was typing it in the calculator. 384 plus 1, right? 385, which is going to go over, times 100. It's greater than or equal to table data. Okay. So if we don't want to expand when we exactly round, we could like subtract 1. That's all. All right. So we have some high numbers, but we expect those for 0.75, right? So if we go to like, or 7.4, I think they're going to be similar. They're a little similar. What about 7.6? 163, 164, right? 7.5. Yeah, so there isn't a singularity there. This all makes sense to me. That's monotonic, that's fine. But at 50, nothing happens. Were we actually resizing and my assertion wasn't going off for some reason? Because now the only difference is now we're minusing 1, right? So look, here we go. 1, we expect that's the right number. Okay, so if we take out the -1, let's make it -0. All right, now we'll compile and we get 2's. So it has to be expanding the table. And then we're not catching that. Like what? What? And that would explain why the collisions are double what you expect, because when we expand, we get a bunch of extra collisions. It's weird that it's exactly double, because you would think an emptier, I don't know. Okay, this is fine. it's at least, it looks like an artifact of our test rather than a bug in the hash table. So the question is why, okay, now we do cowabunga oriented programming, where when we do this, we're going to log cowabunga, right? Whoops, let's print. Basic, let's import basic. I'm just going to print to be super dumb. So we're cowabungaing, import. Do I know my own programming language? Sometimes the answer is no. So we're cowabungaing every time. What is going on? Why? Okay, we init the table. We do this. I wonder if there's a pathological case when the load factor, guys, I bet when the load factor is 50, we do some math to determine the new table size and we accidentally get the same size. Which is why it's double the number of collisions, because we remake the same table at the same size. That would be a bug in the hash table, right? Okay. That explains why our assertion isn't going off, because we're doing a resize to the same size, bro. That's like some next level 4D chess shit right there. You know what I'm saying? That's like 5D chess. Okay. So when we expand, oh, we do this on purpose because we think this is totally broken. This is totally broken. Okay, I thought the logic here was if we're gonna double, blah, blah, blah. But I didn't account for the load factor here at all. So this is supposed to get rid of our, or decide that we don't need, okay, if you do a lot of removes, you would be filled with tombstones and stuff, but you don't need to get bigger because you just rehash and get rid of all of them. And that's what we think is happening for low load factors, because we're not checking the load factor here, right? Okay, so so we want desired slots is table.count times 100 divided by table.load factor percent, right? Plus 1. I should really it should really be the same code as this, I guess, but I don't know why we put the plus 1 here. because there's no divide, that's why. Let's just do this. Let's just say if table.count times 2 Okay, we'll explain that a little bit more later. Okay. Now I broke it. Okay, hold on. This might be a thing. Yeah. No. So 51K. Oh, you know, we don't. We don't want the times 2 here. Do we? Maybe we do. But this is like, oh, because we took out the -1. All right. Right. Okay. So this all makes sense. Our load factor is 50%. If we add exactly 50%, guys, we're going to go over. Is our load? Yeah, it's 50. Okay. If it's 25, yeah. So we trip a resize if we go a little bit higher, right? If we take out the +1, the -1. We just barely trip a resize with the last element, but it doesn't really generate that many more collisions anymore because it's actually a bigger table now, I think, right? Well, yeah, but you see, it goes from 0.6 to 0.9 instead of double. And the reason is because we're actually rehashing into a bigger table and changing the size. And now that we're changing the size, our assertion goes off, right? Remember, the mystery before was that our assertion was not going off. And it was not going off because we were resizing, but we were resizing to the same size. So the mysteries are solved. This is totally broken after using the code for years. I mean, welcome to computers, man. I don't know what else to tell you. Have you been here to computers before? All right, I think this is good. This is a dramatically better hash table than it was at the start of the stream. And it's all because our network storage device beeped at us a lot. Are there any questions about what we did here? Because it might be about time to end the stream soon. I don't know how long we've been going. This is good because it'll make the game a little better. 3 hours, yeah, that's a good stream. It'll make the game a little better. The people will get a better hash table and all this stuff. Now, the mystery is, guys, here's what I don't understand. Is Jimmy Wales seems to be telling us that we're supposed to get more collisions as we go back up, but we are not necessarily getting that, right? So let's do a release build of this. It's going to take a little bit. Let's comment this out for now. It's chugging away. Like, it does go up. But it went away when we switched it to random. That's the thing. We discussed the hash function. No, everybody rat holes on hash function, but all the stuff we fixed today had nothing to do with hash function, all right? There are plenty of other things that could be causing problems in your hash table besides the hash function. Hash function in this case is actually up to the user anyway. You like plug one in if you want. So here it goes up, right? But again, I think if we swap out our random, where was it? Here, if we swap this out, we'll get many fewer collisions and it stays level, which I kind of don't get. In fact, it goes down slightly. This part I don't understand, and I don't know if it's because the random does something to make it completely uniform, or if there's a different problem. Okay, so this is a thing to think about. Like, I don't understand this here relative to both this. So this is not that surprising because maybe when we advance our probe, we should do something more sophisticated than this. I don't actually know. Okay, so that's fine. But the fact that this is completely flat and shows no growth as the table gets bigger confuses me a little bit. If you use h of x is equal to h of y and then g of x and g of y for probe offset, you decorrelate x and y. Okay. I mean, this is kind of a g of x, but maybe it's not randomizing enough, right? So we still retain some correlation. This is still much better than before we used it. Okay. Now, instead of g of x, like I don't want to require the user to supply two hash functions. That kind of sucks, right? So we could just like rehash their hash. I don't know if that's good. But I'm surprised then by the fact, so if we don't get more growth in collisions when that happens, why, then what is the deal with the birthday problem scenario? Like, this sort of seems to be telling us that we should have more problems unless somehow this goes up at one rate, but then the average goes up uniformly. I don't actually understand that part. It's called double hashing here. Yeah, I'll go read that. I'll go read that. Yeah, so this is weird. The birthday problem is about expected number of first collisions, not expected number of total collisions. Right, I agree with that. But that's a very weird thing because it's like, it means somehow the other side of the distribution changes in an exactly inverse way in order to compensate, right? Which is unintuitive, but I guess I can picture that. All this is unintuitive, right? The birthday problem seems weird because it is concerned about one collision, right? But if one collision happens earlier, under some circumstances, you wouldn't necessarily expect then there to be, like you would expect more collisions to also happen earlier, right? The second collision would also happen earlier, and the third, like I don't understand. Like at some point, it has to reverse course and things happen later, and I just don't see the mechanism by which that would happen. It doesn't make sense to me. Like, you can add in this correction term or whatever, but this isn't going to change your result. It's basically the same graph. Boop. Well, I have more to learn about this, so that's interesting. So I think that's where we're going to end the stream. Thank you, everybody. I am going to start going about the rest of my day for a while. Do some other work first, probably, and then go to an appointment and all that. If you missed parts of this, we'll probably put it up on YouTube later, although maybe not, because here's what I'm worried about. Is I started at the beginning talking about birthday paradox stuff, and I don't remember exactly what I said. I mean, we said a lot of other stuff about hash tables, but like at the end, we're like, wait, that doesn't mean what I thought it did. And you know, people don't, if you put a bunch of stuff on YouTube, they don't watch the whole thing, right? So if they watch the beginning when I say, oh, I expect the number of collisions to go way up, then that may just be the takeaway that people have. Although, maybe I didn't say that until way later into it. I don't know. Anyway, maybe we won't post it. All right. Thanks, everyone. See you later.